All righty. So chapter 2, we're finishing up chapter 2 of our NASM PowerPoint on basic exercise science. We've been talking about the kinetic chain. We kept it kind of simple when we were just talking about muscles and the skeletal system. Well, today we're going to get into a little bit of the deeper parts of anatomy, a little bit more complicated as we talk about muscles, because that's obviously a really big part of our sort of job, our career. And so after this presentation, we want you guys to understand like the structure of all the little tiny moving pieces that are in our muscular system and how it actually functions, and then the endocrine system as well. And then most importantly, how both of these systems actually adapt and how they respond to stress and exercise. So minimizing that, put me there. All right, so actually, so if we're looking at the muscular system by definition, just because it's always kind of nice to start off with like a clear definition, it is a series of muscles that are under the control of your nervous system and is designed to generate internal tension in order to manipulate the skeleton. So what happens within like a muscle is that all of the special little fibers that are in that muscle are able to contract, and that draws both ends of the muscle inward. And because your muscles are attached to bones on both ends, that's what causes your bones to be manipulated, right? So again, this is kind of a classic example of like one of the things that I always like to tell people, which is that like if you want to understand how like the universe works just a little bit better, just always remember that function follows form and form follows function. They are absolutely directly related to one another. Your muscles have special contractile proteins in them that we are going to spend a lot of time talking about and understanding today. And that's actually what allows all of the work to take place. Like because of those contractile proteins, your muscles are able to drag your skeletal system around. I mean, if you look at like, even we just look at like this picture here, you can see the upper traps, right? That's this group of muscles right here. So they're attached on the top of this ridge that's on your scapula, and then they're attached at your spine here and a little bit over here. So like when this muscle fiber contracts, these upper fibers draw your shoulders up this way, and these lower fibers, they also kind of draw it upwards. I mean, obviously there's kind of an upward angle there, but they also kind of pull back a little bit, but they're not super great at retraction of the shoulders. And that's where these muscles right here, which are mid trapezius muscles, they actually pull inward. And then the lower trapezius muscles, you can see they're attached on the bottom. They pull downward. And so now we've got these three trap muscles, one that goes this way, one that goes this way, and one that drops our shoulders down. And so that's dragging all of those bones around because all the special little proteins within that muscle. But like I said, it is a interdependent system with the rest of the kinetic chain. And so we do know that like all of this is under the control of your nervous system. And so if any of those systems are out of whack, it's not going to be able to move the way it's supposed to. So when it comes to a muscle, so this is where you look at this freaking, bear of a PowerPoint slide here with a lot of text on it. We're going to see a couple of these today because it does get a little technical. But if you look at like what a muscle is, right? So an individual muscle is a little bit, it's if we use like our kind of traditional anatomy terminology here, each muscle is its own individual little organ. Like that's a lot of people think of like organs. You generally think of like your stomach or your heart, your lungs, small intestine, large intestine, pancreas, stuff like that, but if you look at the actual sort of like definition of organ, it's any like lump of tissue that comes together to function in a specific way. So I would argue that like each of your individual bones is its own individual organ. I would argue that every muscle that you have is its own individual organ as well. And those organs, those little like those bundles like that make up like that individual muscle are comprised of layers upon layers upon layers. They are a bundle of a bundle of a bundle, basically. And so when we're looking at the way like muscles actually bundle up, they're kind of like a rubber band ball, like My mom used to love these things. She would always like buy like starter ones, and she just had like a bunch of them. But like she would use rubber bands all the time for stuff at the pet store, and she loved like rubber bands ball, and we thought it was such a like goofy thing that she was like into, but she just like kind of loved like creating them and then like unwrapping them and using them and stuff. But all of this is like a bunch of like individual layers. Now imagine if we just change this up slightly and we just use like blue rubber bands on the most innermost layer, and then we use like yellow rubber bands that are comprised of a bunch of little blue ones, and then we used like a big one, which is a whole bunch of them all coming together. That would sort of show you the arrangement of how our muscle fibers work. So if we look at like we look at what's called a fascicle, okay? A fascicle is a bundling of individual muscle cells. So this is like my favorite picture for showing you this. So you can see here, this is the overall muscle itself, right? But right here, this little like tube that's pulled out at the very end, this is an individual muscle fiber. Okay, that's an individual muscle cell all by itself, separated from the rest of the crew. So what a fascicle is, like the rubber band ball, is that it's a bundling of several muscle fibers, right? So we've got 1 here, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 20, 25 muscle fibers, all bound together in this one bundle right here that we call a fascicle. And then each muscle is comprised of, you can see like 1, 2, 3, 4, 5, however many fascicles happen to be in that overall muscle. So if we're working our way from the outside in, the outside layer is the first bundle is the actual muscle itself that's wrapped in a layer of connective tissue that we call fascicle. So I'm sorry, fascia, right? So a muscle is a bundle of fascicles wrapped in fascia, and you can see that here, right? See this little like clear wrapper that's kind of wrapping around the outside here? That's the fascia. So you guys have actually probably seen fascia before. You've probably seen fascia if you've ever been cooking and like you've been making like steak or something, and you get that like silver skin that's on there, or like chicken, you'll see that like kind of like shiny outer layer sometimes on like a chicken breast. That's the fascia of whatever muscle that happened to be. And so fascia is like connective tissue, right? It's connective tissue that surrounds our body. So if we look at like fascial systems in the body here, you can see they're actually kind of wrapped in very specific ways. There's kind of these very interesting routes that it tends to take. You've got like a fascial system that kind of covers the front here and like your quadriceps and your lower leg, right, back, and all this. And then like there's some sideways ones as well. And then there's some that actually wrap like this, and they kind of pull at an angle like that, creating stability on both sides. And then when you put them all together there. So that's sort of like all the different fascial systems. But if you look at what fascia actually looks like, it's this really like stringy, it looks like friggin' spider webs in a way, right? And that fascia is what keeps our muscles from like getting tangled up, because again, these are just like bundles of contractile proteins, right? And when we look at like how muscles will contract, sometimes it causes them to kind of bulge together. Like if I took a muscle that was this long and I pulled it like this, like all those fibers, they might get like intertwined or tangled up. And we don't really want that to happen. So we need to have a layer of connective tissue separating all the bundles. Actually, here's another really great picture. I kind of like that one better. Gosh, oh, good. It's not downloadable. Give that a shot. So that's the outermost layer itself. It's the muscle, which is a bundle of fascicles. Now, again, like what a fascicle is a fascicle is a bundle of individual muscle fibers. So the next bundle layer is a fascicle that's wrapped in its own connective tissue. So you can even see that here, right? If we look at this fascicle here, you can see this outer kind of thin layer, right? That surrounds the whole thing. That outer thin layer is what's known as your paramecium. And that is the layer that kind of separates each of the individual little fascicles. And there's blood vessels and lymphatic vessels and things like that that are running throughout all of the individual fascicles and stuff. And that's great because that delivers oxygen, and nutrients to our muscles, which obviously we need to grow and survive. But like, we need to have like a good, clear separation between each of these, right? And then, we can see the individual muscle itself. And so our final layer here is if we look at like each fascicle is made up of individual muscle fibers, and each of those fibers has a wall around the outside of it separating it as well. And so here's the individual muscle fiber. Now you might be noticing by now that this still pairs down one time even smaller, right? Like this is the individual muscle cell that we're showing you here, right? But look, there's another rod projecting from that. That's what's known as a myofibril. That is, we don't necessarily consider it its own, like it's not a cell. It's not like a bundle of cells. It's just a protein. And it is the individual like proteins that are running from end to end in every muscle cell. So if you look at like a classic, go back to high school biology and just look at like a classic animal cell, we remember all the general organelles that are in an animal cell, right? We got the nucleus, we got the that's the brain of the cell. We got all the fluid that's in there. That's the cytoplasm. We got the little like mitochondria. Those are the energy producers. And then we got like, all this like what we call like the endoplasmic reticulums. We got little lysosomes. We got all these like little organelles. Well, every cell in your body has all of those organelles, with the exception of like red blood cells, but we'll talk about that later. But every cell in your body has all of those pieces, but they all have a special shape. They all have a special form, which allows them to function in a very specific way. And so that is where, when we look at this individual muscle cell here, you can see there's the mitochondria, right? 1, 2, 3, 4, 5, 6 little mitochondria. You can see the little purple nucleus there. I don't know why they're drawing that one in purple, but like the rest of the nucleuses, they're kind of drawing those in red here. So you get like a whole bunch of nuclei. And then, this is like a little capillary that's kind of running throughout the whole area as well. So yeah, we're seeing like all the normal stuff you'll see in a cell. And then look at how much space is between all those myofibrils. That's cellular plasma. That's like fluid, right? But the special thing that muscle cells have that none of the other cell types have this is that it has these myofibrils in it, okay? And these myofibrils are little proteins that are tied end to end to end, and it consists of other little proteins in it. So you can't really see it, but if I zoomed in like crazy here, you'll notice it's got some little like stripes on it and stuff. And that's really where all the magic of muscle contractions actually takes place. That's the microanatomy that we're going to be looking at today. We're going to talk about how those proteins are able to bind to one another. So here's a different picture, right? You can see the outermost layer of the muscle itself surrounded by fascia. A muscle is made up of a bundle of several fascicles. If we pull one of those fascicles out, you can see that that is a bundle of several muscle fibers. If we pull an individual muscle fiber out, you will see that it is made of all kinds of little myofibrils. So bundles on bundles on bundles. So you kind of want to get a working definition of each of these things, right? A muscle is an overall bundle of fascicles. A fascicle is a bundle of muscle fibers. And a muscle fiber is the fancy term that we use when we're describing like muscle cells, okay? And what a muscle cell is it's a series of these little proteins that we're going to talk about here called actin and myosin. And then every muscle ends in a tendon, which is like the connective tissue that attaches your muscles to your bones, that allows your muscles to kind of drag around your bones. So this is a picture that I have kind of a love-hate relationship with, because like we actually showed this picture yesterday when I was talking about ligaments, right? You can see this is connecting this femur to the fibula here, right? That is your LCL ligament, your lateral collateral ligament. And it's there to attach like those two bones on the outside, right? We draw it in white because it's representing that does not get very much blood flow, and that repairs much more slowly. But if you look at the rest of this picture, look at how much muscle is kind of generally connected, and it kind of gets white at the ends there, right? And then look at this quadriceps muscle here. This quadricep muscle actually runs all the way down, and then this makes it look like it's attached to the patella here, which it actually runs over top of the patella and then inserts right over here. So this whole section here is very white. That's your patellar tendon, right? Or your quadriceps tendon. And so like that it depends on who you ask. Like I think it's all one big thing, but like some people you can see they kind of separate the two different sections of it, but it's attaching a muscle to a bone, right? That's what makes it a tendon. So again, we want to make sure that we don't get our ligaments and tendons mixed up. Ligaments attach bones to other bones. Tendons attach our muscles to our bones. So every muscle will end in a tendon. Which is important when we talk about like the anatomy that we mentioned yesterday, when we're trying to remember like what our nervous system's connection to our muscles is, right? It's got the muscle spindles and it's got the Golgi tendon organs. And those two things are sending information to the brain saying what length the muscle is and how much tension has been developed in it. So how's everybody following along so far? Any questions? Checking in with everybody.
No questions so far.
All righty. Cool. All right. Well, let's take a look at, let's zoom in a little bit. Let's talk about the individual muscle fibers. So we're going to spend a little bit of time on this. But if we look at like, because this is something they do want you to know. This is the more technical stuff that they are going to spend time quizzing you about on your NASM exam. With some of the more technical information, it's like a lot of like, it's microanatomy, you know what I mean? Like it's you definitely cannot see this without a microscope. But it is really, really cool how all of this works. So hopefully you guys find it somewhat interesting. So as we look at an individual muscle fiber, one individual muscle cell, again, here's the muscle, right? It's a bunch of fascicles. That's a fascicle. That's a muscle fiber. So look at this muscle fiber here. You can see all of this like kind of specialized, all these like little specialized structures that are in there. Now this picture didn't pull out one of the myofibrils. This didn't pull out any of it. Like you can just kind of see the ends of them here, all the little dots that are on the inside and like these little tubes right here, right? Those are the individual like little myofibrils. These little circles here with all the dots on them are where the magic of contraction actually takes place. But look, you can also see this kind of weird webbing that's in there. That webbing is actually a specialized version of what we call the endoplasmic reticulum. So which is normally this little like kind of wavy, sort of weird looking wall stuff that's on the inside of our cells, right? So right here you can see it's kind of like interesting, like little like webbing here. That's called the endoplasmic. Endo means inner, so this is taking place inside the cell. What's interesting about like muscle cells though is that we have kind of a specialized version of that reticulum that we call the sarcoplasmic reticulum. And the reason we call it the sarcoplasmic reticulum is because it's taking place, this lives in this fluid right here, which is a specialized version of your cellular plasma that we call your sarcoplasma. So now we're starting to see sarcoplasma, sarcolemma, sarcomere. We're starting to see like a lot of terms that have the prefix sarco in it. And then we also see a lot of things like myofibrils. We see a lot of prefixes of the word like myo. And that's because both of those words kind of mean muscle. Like sarco actually means flesh and myo means muscle. Both of those are sort of our prefix. So whenever you guys see those terms like sarco or myo, you're probably in muscle territory. And that's going to help you kind of understand where you're at and know that we're probably talking about like muscular contractions or proteins or things like that. So that's this kind of interesting webbing here. And what that sarcoplasmic reticulum does is that it transmits things like calcium and other materials throughout the entire muscle cell. And we'll talk about why that's so important in just a second. So typical cell components you are going to see just like in any other animal cell, right? A muscle fiber It's an individual like muscle cell. You've got your cellular plasma, which is the fluid. All of your cells are basically like a wet, swampy environment, and there's a lot of fluid within them. And so the cellular plasma that's in our muscle cells, we call that sarcoplasm, just because it's muscle fluid, and it's this liquid material. The reason it's kind of specialized because it has like a lot of glycogen in it. That's basically carbohydrates that we can use for energy. It's got a little fat in it, so we can use that for energy as well. Some minerals like sodium and potassium and calcium, like little electrolytes that help us create energy and contractions and stuff. And then it's got this specialized little protein in it called myoglobin, which actually carries oxygen throughout the muscle cell, which is pretty great. So that's what the fluid inside of every one of your cells is. So now that we understand it's kind of this like wet kind of fluid area, it makes a little bit more sense as to like how all these materials are able to actually kind of transport and move around. All the liquid stuff is able to kind of move throughout our muscle cell in order to create these contractions that we're about to get into. Now you're also going to see mitochondria. Mitochondria, the energy producers. We're going to talk more about energy production tomorrow. But basically your mitochondria is able to take things in like the glucose that's found in glycogen and spit out a bunch of energy in the form of ATP. So that's a big energy producer there. And because your muscles use so much energy, guess what? They are filled with mitochondria. But it depends on like what type of training you do that will sort of determine how much mitochondria you actually have, which is kind of fun. Like for instance, if you do a lot of cardio, the muscle that you build will have lots of mitochondria in it, so that it will be really good at like long duration energy production. Versus like if you do a lot of sprints, what'll happen is your body will actually produce energy outside of the mitochondria in that sarcoplasm fluid. And so what ends up happening is like your muscle cells grow in size because they're packed full of more fluid. So those are two very different ways that we produce energy and two different adaptations to exercise. That's part of the reason why, and we're going to look at this at the end of our lesson today, but there's a difference between type 1 muscle fibers and type 2 muscle fibers. They look structurally different. If you look at a runner versus a sprinter, oh my gosh, I can't type today. What? You look at the difference between these two, it's a pretty stark contrast, right? I mean, that guy's a lot more muscular than that guy over there, but they're both athletes, they're just very different type of athletes who have developed very different energy systems and different muscle cells. Their cells would actually look different. This guy here would have a ton of mitochondria in his legs and calves, right? This guy over here has a lot of cytoplasm and myofibrils in his legs. And so very, very different athletes, but definitely both very valid. So the mitochondria is the energy producer, and then the nucleus, which is like, usually like the brain of our cell, right? The reason I say it's the brain of our cell is because it's the command center that contains all of your DNA. And your DNA is a blueprint for how stuff is going to get assembled, and other materials, right? So what's really cool about like nucleuses, or nuclei, I should say, is that they contain all of our DNA. But in a muscle cell, we actually have a lot of extra nuclei, which would normally be a problem, right? Like in your heart cells, for instance, when we get to the cardiovascular system, your heart cells are also muscles. It's also very muscular. It has the same proteins that we're talking about here. But what's interesting is it has less nucleuses within those muscles, right? It just uses one to kind of control a very large area. And that's because we need our heart to contract all at the same time and be very in sync with itself. Because if it ever gets out of sync, it's not going to be able to generate pressure as well, and we're not going to be able to pump blood throughout the body. So we'll see less nuclei there. But in muscles, we see a lot of extra nuclei. Now, why do we see so many extras? Well, because they have our DNA in them, they're actually able to kind of shape themselves in whatever shape they need to get to, right? So when you're experiencing hypertrophy, which is muscular growth, right? Because you have so much extra nuclei, those nuclei are able to become whatever type of cell or whatever type of material we need in that muscle. And that's what allows them to grow more effectively. And that's why muscles can grow and shrink better than any other type of organ in the body. It's because they have all those extra little nuclei. They got the blueprints for how to do all of it. Does that make sense, guys? Thomas, you got a question?
Yes, real quick. Can you repeat again what sprinters have?
Oh, sorry, Dion. Hold on 1 second. What'd you say, Thomas?
Can you repeat again what sprinters have and what long distance runners have? It's plasma and whatnot.
So a long distance runner will have more mitochondria to produce energy on the go, and a sprinter will have more cytoplasm to create a big burst of energy that eventually gets turned into lactic acid and needs to slow down.
Okay. Is it possible to have high amounts of both? And I only ask because I don't think I've ever seen like a elite sprinter also be like an elite distance runner.
Yes. So not really, because like when you get to an elite level, it gets, you get further and further and further pulled apart. Like I like to consider myself relatively fast when I'm sprinting, but I'm also pretty good at long distance. So I think it's possible at like an amateur level. But yeah, if you look at like pro athletes, like DK Metcalf, right?
Right.
He's one of the fastest guys in the NFL, but he he tried to go up and like he was like, oh, I'm thinking about like trying out for the Olympics so I can be a sprinter. And it was one of those things where I was like, that's never gonna happen. And I was like, what are you talking about? He's such an amazing athlete. I'm like, yes, but like he's an amazing football player, Right. So when you get to the elite level, the separation gets deeper and deeper and deeper. It's just like, Lance Armstrong, despite all the, Lance Armstrong, a lot of controversy, he definitely cheated, but he was still, even at cheating, an amazing like cyclist, right?
Correct.
Dude tried to run a marathon and nearly killed him, and you'd be like, that doesn't make any sense. It's like his heart's got to be really strong. It's like his heart is really strong, but he did not train for that. It's like, I mean, his marathon time was better than mine, but like compared to like what a all-star athlete he is, you would think that like, he would crush it.
Understood.
Yeah. Dion, I'm sorry, I slapped that mute button on you. What did you, do you have a question, Dion? Oh, and you're on mute, just so you know.
No, I don't have a question.
Oh, okay. All right. Okay, so where was I? We were talking about the nuclei, right? So the nucleus is the command center, and your muscle cells have actually got a lot of extra nucleuses so that they can sort of transform into whatever material your muscle needs. And that's why muscles are so good at growing, but also kind of why they're so good at shrinking as well if you don't use them. And then here's the most important part of every muscle cell that we are going to, at least the most important part for us, the myofibrils. So myofibrils are these rods. You can kind of see, these individual rods here that have the dots on the end, and then they're covered in that webbing, that blue webbing there. That's a rod, that's a rod, that's a rod. Those are your myofibrils. And myofibrils are these rods that run end to end in the muscle cell. And then what happens is that rod shortens because it has all these little proteins in it that slide across each other like this and come together. So then when that happens, that pulls the muscle cell in closer to itself, which sounds pretty similar to what's happening in our overall muscles, because that's exactly what does happen. In thousands of muscle cells, all shorten. If they all shorten at the exact same time, the entire muscle shortens. And it's because of all these little proteins. So it's a lot of, little bundles on bundles on bundles. So here is an individual myofibril, okay? Right here, this is the rod that is tied end to end in every one of our muscle cells. And what gives our muscle cells their special ability to be able to contract is this rod right here. Now you'll see the rod is comprised of all these, like you can see the dots on the end here where we're kind of showing like the ends of it. That's actually representing these right here. It's representing like these little lines as they come to the very end every time, right? We're just kind of cutting it in half. So you're seeing like, you know, somebody slice through this section of the line. So these right here, this little section right here between this blue line and this blue line, these are the individual proteins that are found in every myofibril in every muscle cell. Okay. Those proteins are called myofilaments. That's their sort of name for them, right? So myofibrils are the rods that run end to end in the entire muscle cell, and they contain individual myofilaments, which are proteins. They're little contractile proteins that live inside of your muscle. This is actually what you are like eating and breaking down when you're eating like a chicken breast or whatever, right? You're breaking down the individual proteins found in all these things. You just can't see them because they are very, 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 very small. So we want to be familiar with what these proteins are. Now, I know this doesn't seem like something that sometimes is overall relevant. Like it's like, this is some pretty micro anatomy here. But if you understand that, you know, all of this like little small anatomy, it is going to help you understand the big anatomy much better when we talk about like how to grow muscles, because our muscles grow in a couple different ways. We're also going to understand muscular contractions a little bit more deeply when we understand how these rods work. So this is what this kind of looks like. So this area right here and is between this blue line and this blue line. We call that area the sarcomere. And so every myofibril, every rod, has a bunch of different like little sarcomeres in it. And the sarcomere is the section where, you know, stuff actually slides across one another, right? So if I had like these two proteins like this, and then I had them slide across each other like that, right? I'm obviously shortening, you know, the myofibril. And if that happens in all the myofibrils simultaneously, the entire muscle cell will shorten and get pulled end to end. So how the heck does that binding actually take place? How the heck does that sliding action occur? Well, if you look at like this picture right here, you can kind of see this looks like a weird like Dr. Seuss tree, you know, and then you got these like big thin, these thin little strands here. So what happens is each of the little like club little heads that are on this strand, they basically reach up and they grab these thin little strands here, and then they pull it towards the center. So what's going to happen is this strand here is going to get pulled this way towards the middle of the sarcomere. And then this one over here is going to get pulled this way towards the middle of the sarcomere. So the whole thing is going to kind of slide like this. And these proteins are going to, you know, slide across one another. And then there'll be a smaller gap here between the blue line and the end of the little purple bush here. And then there will be a really small gap between the two thin strands here. So that's how actin and myosin are actually able to contract. And so we want to be able to kind of break that down in detail here. So let's take a look at our myofilaments. So if we zoom way in, right? And by the way, here we go. Here's actually, we're still slightly zoomed out here. Oh, that is, we are literally zoomed out. That picture sucked. That's a little better. So here's what this kind of looks like, right? Here's a myofibril, right? And then you can see this area right here, right? See this like little zigzaggy, that's the blue line. Now, our picture in the PowerPoint kind of drew it as like a straight line. In reality, this is actually, it kind of makes a zigzag. It actually kind of gets pulled like this, and then it gets pulled like that, and then it gets pulled like this, and it gets pulled like that. And it creates a zigzag. That's actually why these little lines right here, those are called the Z line, okay? And you can see the reason it is because look at like, here's the little thin strand, little purple strand, and then the next one is slightly offset. And then this one's like here, and then that one's slightly offset. So rather than like stacking perfectly like this, they're just slightly offset like that. And it creates this sort of zigzagging action. That just creates a little bit of extra stability, you know? Like if you were trying to build something, you would want to, you know, give it like a wider surface area so that it wouldn't tear apart. That's part of the reason why we have this interesting sort of Z line here. Now, this area, like I said, it's called the sarcomere, right? Hold on one second. And what's going to happen here in this myofilament is that it is going to contract, and that is going to cause this to slide this way, and it's going to cause this side to slide that way. So the entire muscle cell is going to shorten because every sarcomere within every myofibril is shortening at the same time. We call this whole thing, by the way, we called it the sliding filament model, or the sliding filament theory. And it's because the myofilaments are sliding across one another and shortening towards their middle. So here's what this looks like right here. You can see, like, here's the individual, here's the individual, like, middle strand here. So that middle strand, that really thick strand right there, with all these like little heads on it. I mean, like you can see, it's got all these like little, clubs reaching off of it, right? That's called your myosin. Okay, that's the thick filament. So myosin's the thick filament, and it has little heads that reach up and they attach to the thin filament, which is actin. And that's this little blue strand right here, right? So again, if we look at our picture, right, we can kind of see, look at this thin little strand. See how it's like made up of a bunch of individual little, like, it looks like a bunch of little like balls, right? And they have all these like little like dents on them. That right there is actually what allows these little club-like heads to reach up and grab. These are binding sites, okay? And these little heads grab those binding sites and they're going to drag them this way. So it kind of like, it almost like peels it, right? It's like pulling it like this towards the center. Each head, this head grabs and then it pulls, this one grabs and it pulls, and then like it, and it just slowly crawls the whole thing towards its center there. So the first strand is the actin. Okay, that's the thin filament here, right? So the thin filament, we call that actin. It has binding sites for other myofilaments, such as myosin, to attach to. And myosin is the thick filament that has little heads that grab the binding sites. Okay, and that pulls, again, the Z lines closer together and shortens that area. That area is called the sarcomere. So if we look at like, look at a picture of this actually happening here. The one I want. Again, Google's a gamble. Let's see if this works. Looking for a GIF here. No. Hey, there we go. So that's actually how that's happening. See how the entire Z line's kind of pulling closer together. This is kind of showing you, like, there's the, on the right here, this is the sarcomere right here, right? But then the other sarcomere that's side by side is over there. It's also pulling at the same time. So if that happens, the entire rod gets shorter, right? That's the sliding in the sliding filament model, or the sliding filament theory, as it's sometimes called. And by the way, this is happening, and millions of them, like it's just happening all over the freaking place. Every contraction you make, the ones that are moving my jaw right now, the ones that are moving your diaphragm to keep you breathing, the ones that are moving your heart to contract, and obviously the ones that move to pick up like a really heavy barbell. All of that is happening. All of that's happening because every one of your individual muscle cells has hundreds or maybe thousands or hundreds of thousands of myofibrils in every one of those cells. And on all of those myofibrils are these little proteins, and these little proteins are sliding across one another. Crazy, right? So here's my favorite way to describe this. We're going to use an analogy here. I definitely, will teach this the same way that most people teach this. So these filaments are really attracted to one another. right? Like myosin wants to reach up and grab actin all the time. It has these really attractive little binding sites that it wants to get its hands all over, right? So that it can do this sliding action. So that wants to happen all the time. If we didn't have control of our muscles, myosin would reach up and it would grab actin and it would slide as much as it can, and then it would just hold it forever. In fact, that's actually what's happening in rigor mortis, which is like, you know how like they call dead bodies, they call them a stiff. The reason they call them stiffs is because like when we expire, our body can't produce energy anymore, and so some of our muscular proteins will contract, and then because we can't produce any more energy, because we're not like living tissue anymore, that contraction kind of stays put. And so you'll see like, you know, like if you remember The Ring, you know, they don't, like, she had like her kind of like contorted face. That's rigor mortis, and it's where the proteins are like, oh, awesome, and they bind to each other one last time, and then they just stay contracted, and eventually that's able to kind of relax after a few days and stuff. But like, that is what rigor mortis is. Weird fun fact. I always like to bring that up because like, it is a kind of a good way to understand like how attracted these proteins are to one another. So if they're so attracted to one another, how the heck do we keep them from attaching? You know, like we need to be able to relax our muscles as well, right? Like I don't want to just like slide all my bundles together and like, you know, bunch them all up and then be stuck this way. I need to be able to lengthen my muscle out in the opposite direction. How do we do that? Well, living on the actin strand are these special regulatory proteins. You can actually see them here, right? You see this like thin blue strand. That's actually blocking all the binding sites currently. And you see this little yellow, little puff ball here that's attached to that blue strand. That is able to kind of move that strand around. So when we want to create a muscular contraction, we have to get those two regulatory proteins out of the way. Okay, so those two proteins, the strand and the little puffy thing attached to the strand, those are called troponin and tropomyosin. Okay, tropomyosin is the big long strand, and troponin's the little puffy ball. But they live on the actin strand. They're there to block that binding site so that we can relax our muscles, right? Again, we talk about like rigor mortis, like we can't get those little like blockers back in place. That's really the problem here, and that's why our muscles stay contracted. So troponin and tropomyosin, they're regulatory proteins. So now we have kind of a good analogy on our hands here. We have actin, which has all these binding sites. We have myosin, which has all these little club-like heads that like to grab those binding sites. And we have troponin and tropomyosin, which are regulatory proteins that block the binding sites so that we can't contract. So honestly, it's kind of like a high school dance in a lot of ways, right? Like you think about like high school or middle school, like you had all your teachers there that were chaperones that were like, hey, 6 inches apart. You know, it's like, yes, you can dance together, but like keep it, you know, like at least, I don't know, you know, in the town I grew up in, which is like, you know, very repressed. It was like we had to dance at like full arm's length, you know. And these are like two teenagers that are trying to get all up in each other's business, you know. But the teachers are there be like, take it easy, you know. So actin's got all these binding sites that want to be grabbed, and myosin has all these heads that want to grab them, but troponin and tropomyosin block them in order to keep that from happening whenever we want to relax our muscles. And that's sort of the sliding, you know, that's what's happening in sort of the sliding part of the sliding filament model, you know. Those are all those individual like regulatory proteins. And that's all taking place in the sarcomere. The sarcomere is the area between those, you know, two Z lines, right? The sarcomere is basically, it's this section, you know, it's this section right here. You know, it's kind of where all of this is taking place. And so that is a sliding action. And that's why we call it this sliding filament model, or I mean, when I was in school, we call it the sliding filament theory. We are still studying this stuff. This is relatively new. We didn't discover any of this stuff until like the 50s. Because we didn't have microscopes to look small enough at this stuff. So some of it's still a mystery. But here's what we talked about all this. I know that, like, I know that sometimes this microanatomy stuff is like, I feel like I don't need to know this in order to make somebody lift a dumbbell and grow their muscles. And you would actually be somewhat right. But I think by having a really good understanding of this, you have a deeper understanding of how our muscles grow. Because there is a difference when it comes to hypertrophy, right? If I just look up like hypertrophy, we're just going to see a bunch of bodybuilders. We're going to see a whole bunch of like big muscular folks, right? That's what hypertrophy stands for. Hyper means, lots of, and so we call that like hypertrophic growth. It's like a lot. It's a very large person. There's two ways that we experience muscle growth. There's two ways that it happens. You can have sarcoplasmic hypertrophy, and you can also have myofibrillar hypertrophy. Okay, so here's an individual muscle cell that has not, this is like somebody who's never hit the gym before. They've never exercised. Here on the left, they've never exercised before. They've got myofibrils in their muscles, but their muscle cells aren't very big. And the myofilaments that are in there, those myofibrils, there's not that many. So there's two ways that we could grow the muscle. One is sarcoplasmic hypertrophy. We could just make the individual muscle cell bigger. We could inject, like don't actually inject, but like, we could basically grow the fluid within the muscle cell and just fill it with more and more and more fluid. And the more fluid that it has, as long as it's the right type of fluid, like again, don't, they do have that stuff and people freaking inject stuff into their muscles, which is like a weird thing. But that's like that's a form of like body modification. That's like implants and stuff.
Those guys that inject oil.
Yeah.
Is that what you're talking about?
Yes, that is not what I'm talking about here. This is natural. Like your body goes, oh, we need more fluid in those cells, and it makes the cell bigger. Very different. Did you ever see that video? It's like a YouTube documentary of the guy who like literally exploded his bicep.
Nah, bro.
He like injected it. He was injecting like crazy that synthol stuff. And and then he like, because he's not a doctor and he wasn't being careful, he like, probably had like some type of bacteria or something on the needle at one point and then injected it. So he got an infection in his biceps. And they like, when we get infections, stuff swells up. It is crazy. He literally like detonated his bicep. It's wild.
Oh man.
Ugh. Don't do that stuff. Just work out. Your body will do this. So anyway, so this is a normal muscle cell here. You can see it's got some myofibrils in it. It's got some cellular plasma, but here there's more cellular plasma, right? There's more sarcoplasm. And then over here, you can see there's just more rods. There's more myofilaments. So those are the two ways that we experience muscle growth, right? Part of it is metabolic stress, right? We're seeing that like the sarcoplasmic hypertrophy comes from metabolic stress. So basically you exercise and you create a whole bunch of lactic acid. And that lactic acid basically damages the materials inside the cell because you weren't able to get rid of that lactic acid. You weren't able to use it and like churn it away so what ends up happening is your body goes, all right, well, we need more fluid in order to create more of that lactic acid, but also to be able to process it more efficiently. So it makes more fluid in response. That's your body adapting. Meanwhile, if you lift super heavy weights and so that's like if you take like low rest periods, this is the pump that you've ever experienced. If you've ever been at the gym and you've done like a burnout set or something, and you just feel like your arms are ready to explode because it's just like very puffy. That's the type of workouts that result in sarcoplasmic hypertrophy. But there's also myofibrillar hypertrophy, which is where there's actually just more rods. If you lift heavy enough weights, your body goes, man, we need more contractile proteins. We need more myofilaments in this muscle cell and in that muscle cell and in that one. So it actually makes more rods in the actual muscle cell itself. And that's another way that our muscles grow. So we want kind of a good blend of that. If we're trying to grow our muscles as big as possible, we want to have kind of a blend of sarcoplasmic and myofibrillar hypertrophy, which means we need to lift at relatively heavy intensities. But we also need to make sure that we are not resting for days. We need to make sure we do enough repetitions. And that's how we're going to kind of grow everything, which Dion, Mir, and Thomas, you guys know hypertrophy is kind of in the middle of everything on NASM's OPT model. You know, it's the middle number of reps, it's the middle number of sets, it's the middle number of rest, you know, and that's kind of gives us the best of both worlds, this plus this. Whereas max strength focuses more on myofibrillar, and strength endurance and stabilization focuses more on sarcoplasmic. Joseph and Edwin, that will make a lot more sense later. I'm just kind of jumping ahead because these guys have we've already kind of talked about that, but I just use some terms that were probably a little, you know, but they'll make a lot more sense later. So that's why we talked about this microanatomy, because the more we understand the microanatomy, the more we can understand the physiology of what's going on. And we won't just take our clients to the gym and just pick any random repetition range. We're not just going to pick some random number of sets. We're not going to pick some random amount of weight to lift. We are going to be specific about how we choose these things, depending on what our clients' goals are and what type of muscle we're trying to grow. Somebody tells me they want to be stronger, I'm going to reach into my brain and pull out my knowledge of how my muscles grow and say, okay, if they want to be stronger, they need more myofilaments. Because if every individual muscle cell has more of those, you know, myofilaments, more contractile proteins, they'll be able to lift heavier weight, which means I'm going to focus on lifting somewhere between like 1 and 5 repetitions for probably a lot of sets, because that's not very many repetitions. And I'm probably going to give that person a lot of rest in between their sets, because I want them to lift as heavy as possible every single set. If another person tells me, they're like, hey, I want to, like, you know, tone up my muscles, I want to lose a little bit of weight, and, you know, I want to, you know, really kind of like carve out my arms, well, then I'm going to focus a little bit more on sarcoplasmic hypertrophy, because I'm going to go back into my brain and say, all right, well, what burns the most energy? That means lots of repetitions, you know, probably limited rest. And then if we can grow the muscle cells, that'll make them pop a little bit bigger by getting like a really good, like, pumped up muscle. And so I'm going to probably do a little bit of higher repetition, probably somewhere closer from anywhere from like 10 to 20, you know, 10 to 15, in my opinion, would be great. You start to get into like too many repetitions, then you start getting into cardio, which isn't the best way to grow muscle. So probably focus somewhere between like 10 and 15, or, you know, maybe even just like 10 to 12 would actually be really good. And you know, I'm going to keep it relatively limited rest while still lifting somewhat heavy to build up that lactic acid. So I know that sometimes, like, when we get really deep in the woods with some of this like microanatomy and stuff, it sometimes doesn't seem like it's like super relevant to what we do in the gym. But like, by understanding this, you're never going to be one of those trainers that just picks a random number of reps. This is one of the reasons why some like advanced trainers kind of trash on CrossFit. And for the record, I think CrossFit's actually great for a lot of things. I think they do a lot of good work in some ways. I don't like the fact that it creates a competitive environment, which means people are likely to sacrifice good form for a win, which is never a good choice. You're just asking for an injury. But my big problem with CrossFit is it's group exercise. So it means that, like, they'll have a workout on Monday and then you can come again on Tuesday, but it'll be a different trainer and everybody does the same workout that's just kind of written on a whiteboard. So it's like, if I did my shoulders on Monday and I come in for another workout on Tuesday, oh, and the trainer's like, well, this is also shoulder day. I'm like, all right, well, that's 2 days in a row. I'm not really getting my rest. And then like maybe the next day is like back, and maybe I miss my legs, throughout the week. So I'm not a big fan of CrossFit like that because it's very general. The more we understand microanatomy, the more specific we will be when we choose things because it's all based on the physiology. That's why NASM wants you guys to know this. All right. Questions so far? Any questions about any of those myofilaments or anything like that? I know a lot of you guys have already seen this stuff. We went over it very much in depth in Kines, but questions, comments, concerns? Anybody? All right, we're moving on. Radio silence. Okay, so let's take a look at how the muscle contractions actually take place. So now we got to look at like neuromuscular anatomy. Let's look at how our brain controls our muscles. Now, I will say we're going to actually move past this section pretty quickly. This was also something really relevant in our kinesiology class. It's a little bit less relevant this mod. So I'm going to move through this a little faster. There's not quite as many notes on it right now, but if you feel like I'm moving through this a little bit too quickly, trust me, we are coming back into it much more in depth at the top of the year. So whenever we're generating force in a muscle, we have to get our nervous system to tell our muscular system how to operate. We have to have our brain tell our muscles how to contract, and that's what we call neural activation. So neural activation is what triggers the sliding filament. It creates the sliding in the sliding filament. And you can see that actually happening here. So here's an individual spinal disc, right? And there's a bunch of nerves branching out from the peripheral nervous system. But then there's some other ones right here branching out in the back as well. So remember how I mentioned how there's information going in and there's information going out? So these are kind of traveling down two very different paths here, right? So you'll have a muscle spindle that's in your bicep that starts to realize that, oh, my bicep is contracting. And so it sends this signal into the brain there saying, hey, we are trying to contract this muscle on this side of the joint. Meanwhile, the muscle that's on the other side is getting a signal from the brain that says, oh, well, we should relax the antagonist muscle because we don't want to pull on both sides simultaneously. We're trying to create movement, right? If I pull on my bicep and my tricep at the same time, right, my arm's just going to stay put because I'm pulling on both sides at the same, right? But if I pull on my bicep for a lot and I relax my tricep, or if I pull on my tricep and I relax my bicep, right, then I can create actual movement. So that is what we have. We have sort of what's called an agonist-antagonist relationship. All of your muscles have an opposite because the only thing muscles can do based on the anatomy we just looked at, muscles can only pull. There's not a single muscle in your body that can push. Obviously, I know we have an exercise called the push-up, but what the push-up is that's my pectoralis muscle pulling my humerus this way, right? And that's my triceps pulling my elbow this way. So if those two things happen simultaneously, yeah, I will push up from the ground, but it's because this muscle is pulling and this muscle is pulling. Muscles can only pull. How do I get back the other way? Well, then my other muscle pulls. This is one of the reasons why people don't understand why they can't increase their flexibility. People are like, I stretch and I stretch and I stretch and I stretch, and I'm just not getting more mobile. And it's like, well, you're only focusing on loosening one side of a joint. You need to pull yourself back the other direction. You need to pull yourself in the opposite direction rather than just loosening up one side of things, We'll look at that here more in depth. So all of this is under the control of your nervous system. So when it comes to generating force in a muscle, you have what is called a motor unit. A motor unit is a single motor neuron. So remember, motor neurons go from the brain to whatever site they're affecting. So this would go from the brain to my whatever muscle I'm trying to contract. That is the motor neuron. And then all of the individual muscle fibers or muscle cells that it stimulates, it innervates, right? So if we look at a motor unit, what we're going to see is a neuron, right? Actually, these are three. That's a picture of three neurons. Hold on. I want a more simple picture. So we'll have like an individual neuron, which you can see here. And then it's going to have its big tail, and it's going to have all its, and then it's connected to, let's see, we got 1, 2, 3, 4, 5, 6, 7 fibers here. So 1, 2, 3, 4, well, they only drew 5, but this neuron is connected to five individual muscle fibers. So that's a relatively small motor unit. You might have motor units like that, like in your eyeballs, for instance, like moving your eyes around, you know, one little neuron that's kind of controlling, you know, these fibers that contract your eyeballs this way, but then there's another one that controls them that way, you know, like, and it creates these different like little tiny contractions. But you could have thousands of motor units, a neuron that contracts thousands of muscle fibers in your glute muscles, for instance, right? That's the largest muscle in your body. So that's what a motor unit is. It's an individual neuron and all the individual little fibers that innervate. So if we zoomed in, right, we would see this little wire would branch out and it would zap a whole bunch of different muscles simultaneously. So if we're talking about that whole neural activation, what's going to happen is an electric impulse is going to travel down the central nervous system. It's going to start in my brain, travel down my spine, and then it's going to branch off from whatever spinal disc it needs to travel down the highway to get to the muscle that it's going to actually contract. And so when that impulse actually reaches the muscle, it will zap that muscle fiber with a little bit of an electric charge, and that will actually cause the contraction to occur. So that is what we call the sliding filament theory, or the sliding filament action. It's where neural activation triggers the sliding of those proteins. And you can see a picture of that here, right? Look at how long the sarcomere is here. But if my brain got a signal to my bicep that zapped those fibers and caused this contraction to take place, that is actually how, you know, how that's going to happen. Now, what actually happens there? Remember, we have the chaperones in place, right, that are blocking all the binding sites. So really what's happening is when a neuron zaps my muscle cell, it basically flushes a whole bunch of calcium ions into the whole area there. And that's what moves those chaperones away. They are really attracted to calcium in the same way that like the myosin heads are attracted to the actin's binding sites. Troponin and tropomyosin, those are the regulatory chaperones, little proteins that live on the strand that block the sites. They are really attracted to calcium. So when my brain tells my muscle how to contract, my brain tells my muscle to release any of its stored calcium into the area. And then that lifts those chaperones away and the contraction can take place. And then how do we flush it out? Well, we basically bind another protein and that flushes all of it out of there. So that's the sliding in the sliding filament theory. It's all based on that neural activation. Now there is a little bit of what's called excitation contraction coupling here. This is going to get pretty complicated, but basically this is going to walk you through the entire sliding filament action. So like a nerve impulse travels down, and then it gets to the synapse between the nerve and the muscle. And then it releases this chemical called ACH, it's acetylcholine, across the little gap. It binds the muscle. The muscle sends an electric impulse across the fiber. That electric impulse releases calcium. Calcium moves the troponin and tropomyosin. Now the binding sites are exposed. Myosin reaches up and pulls actin towards its center, and it slides. And then when a new molecule of energy attaches to that, that causes the calcium to get flushed out, and that causes the proteins to go back in place, which causes the unsliding to occur. And that is the whole process. Very, 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 very complicated, but definitely something we will talk about in later classes. But just in case anybody has any questions about it, any questions about how all that worked, how the nervous system was sort of interacting with the muscular system?
No, I'm clear.
Love that. Thomas, by the way, this is the last time you're going to hear me go through this whole thing.
I hear you.
I mean, you're going to have to hear it from Mo, but it's the last time you'll hear me say it.
Right.
All right, so let's take a look at our different muscle fiber types. So let's zoom out, guys. We've been zoomed in so far, so long for this PowerPoint, right? Let's zoom out now and take a look at, what our muscles actually kind of look like to the naked eye, So we do have sort of two different fiber types in our body. We have type 1 muscle fibers and type 2 muscle fibers, and we just name them or we observe them, we label them based on how they look. It's just their general characteristics. So like muscles are going to have different characteristics that allow them to have different types of strength, different types of energy production, and then obviously like visual, tangible physical differences between them. There's going to be type 1 and there's going to be type 2. Type 1 muscle fibers. We call a type 1 muscle fiber, we call them red fibers, or we call them slow twitch fibers. And what I mean by that is these are the muscle fiber types that are really good at contracting for a little bit of force a lot of times. So these are your endurance type fibers. They tend to be a little bit smaller in size. They don't produce as much force as your type 2 fibers. And they're usually the muscles that are associated more with like stabilization, or they're more associated with like endurance type activities. But what's really cool about them is they actually have increased oxygen delivery. There's more capillaries running throughout the entire muscle. There's more blood vessels, which gives them increased oxygen delivery. They also have more mitochondria. Those little like pills that create a bunch of energy within our cells, right? Type 1 muscle fibers have lots of mitochondria straddled throughout the whole thing. So they're really good at producing energy with the use of oxygen, which is one of the reasons why we have more capillaries in red blood cells, because more capillaries means more blood means more oxygen. And then the mitochondria uses that oxygen to produce more energy. And that's why they have a lot of endurance. They're able to do a lot of work over a really long time. They're very slow to fatigue. These are your long-term contractions. So again, look at a picture of a marathon runner. We're going to see long, very lean muscles, right? That are really good at contracting for a little bit of force over 26 freaking miles, even like a lot of like, I consider certain like calisthenic athletes, right? Who can do just like, 200 push-ups in a row without getting tired. That is a type, they have a really good amount of energy there. Now, their pec muscles are primarily type 2, but they've trained them in a very type 1 way. So this kind of depends on what type of athlete you want to be, if you want to be, like a basketball player, you need to have kind of a blend of type 1 muscle fibers so that you're going to have plenty of endurance, but you also need to be pretty explosive. So that is where our other muscle fiber type comes in. So we also have type 2 muscle fibers, which are fast twitch muscle fibers. These tend to be much larger in size. They tend to produce way more force because of their larger size and more myofilaments. They are associated with like max strength and power type contractions rather than endurance or stabilization contractions. But the problem with fast twitch fibers is that they are generally pretty quick to fatigue. They tend to get really tired really quickly because they don't have as much mitochondria in them. So they have less mitochondria than the type 1, which means they're not quite as good at producing energy. But they do have more cytoplasm. They are like larger in size. They have more of that sarcoplasmic, they have more sarcoplasm, cellular fluid within them. Now, type 2 is going to further divide down into type 2A and type 2B or type 2X, depending on who you ask. And that is the Type 2A is like high oxidative fast twitch fibers. I like to consider type 2A as sort of a blend between 1 and 2. It's like they're pretty big, but they're not like as big as like a full explosive muscle. They're pretty strong, but they're not quite as strong as a full explosive muscle. They've got a pretty good amount of endurance, but they don't have as much endurance as like a type 1 muscle. So honestly, guys, when we're thinking of most of the sports that we watch on TV, basketball players, football players, soccer players, baseball, those are athletes who are generally focused around type 2A muscle fibers. Like you think about like LeBron, right? He has to be super explosive to be able to like move as quickly as he's able to. And he has to be able to like, obviously dunk a basketball, which involves like a really strong jump, and he's got to be relatively explosive. So I'm not saying that he does not have, true fast twitch muscle fibers like type 2X fibers, but he also has to be able to use those same muscles to run a whole bunch of minutes during a basketball game. Football players, right? Similar concept, right? You look at like a wide receiver and how much running they have to do compared to like a lineman. A lineman is just going to do a really big explosive. They're going to work for maybe 5 to 10 seconds while the quarterback gets rid of the ball, and then their job is done. Whereas like a wide receiver might be, or like even a running back, they might be doing something kind of explosive and like they're trying to get going for, maybe even 30 full seconds. That'd be a long play, but like, they're going to have a little bit more, a slightly bit more of endurance. So and then soccer players, they're constantly sprinting and recovering and sprinting and recovering over and over and over again. So, that is very much the difference between type 2A and type 2X or type 2B. Type 2A is kind of in the middle. It's relatively oxidative, but it's still a fast twitch fiber, whereas type 2X is not oxidative at all. It runs out of energy quick, but the energy that it does have is super explosive. So if we start to think about like a duration situation here, right? Let's see, I'm gonna do something I've never done before. Let's try this out. Go back to paint here. Make myself a little.
I had a question.
Yeah, please.
So can a type 1 fiber turn into a 2, and can a type 2 fiber turn into a 1? Or
yeah, through like, training.
Yeah, through training.
Yeah.
So that's like, okay. So a type 1 can turn into type 2. Type 2 can turn with different types of training.
Right? Yeah. So remember our principle of specificity, right? Like our body will adapt to whatever type of stress we put on it. So if you took a marathoner, right? Now here's the thing. You would have years of marathon training. And so like fighting against those genetics is going to be pretty freaking tough at that point. Because like, their body has adapted to one style of training for a very long time. And then we're trying to change it. But let's say like a marathoner, like I can't remember, Ulid Kipchoge, right? Fastest man in the world right now. I'm sure I butchered his name, but he if you took this guy here, he is the guy who ran the sub 2 hour marathon. He ran 26 miles in slightly under 2 hours, which is insane. If you were to take him and be like, all right, we are going to focus entirely on lifting really, really heavy weights, and we're going to eat like crazy. And, we'll have some workouts that are moderately heavy with limited rest, and we'll have some workouts that are really heavy with lots of rest. So we're working on sarcoplasmic and myofibrillar hypertrophy. Eventually, you would be growing more type 2 fibers, but yeah, you'd have a pretty uphill battle doing that. The same thing would be true of a bodybuilder. If you took a huge bodybuilder and you just made them like do endurance training and nothing but endurance training, eventually their body would adapt to that. Your body will adapt to whatever type of stress you put on it. Because basically, if we took the marathoner and the marathoner turned bodybuilder, right? Their body goes, wow, we're trying to lift heavy weight all the time. We need more muscle mass, right? And it's like, oh, and we're getting lots of calories. in surplus, we can grow that. We've got the energy necessary to grow that muscle mass. So then the body is going to increase in size. The muscles are going to get larger. Now, if you took the bodybuilder turned marathoner and you were like, you know, they start jogging consistently, maybe at first they can only run maybe a mile or 2 miles, you know, because they just don't have that cardiovascular endurance. Their body's going to go, man, we need more mitochondria. We have all this cellular plasma, but that only gets us about 30 seconds worth of energy. This guy's trying to run a couple miles. That's going to take minutes. We need to produce more mitochondria, more myoglobin, and we need to have longer, leaner muscles. So we'll start developing that type of adaptation. Your body will adapt to whatever you place on it. This is one of the reasons why it's so important for us to have different blends of exercise training throughout the year. Does that make sense? Answer your
yeah, I got it.
So this is what I consider. So slow twitch fibers, I would consider that to be, hold on 1 second. Hold 7. So I would consider slow twitch fibers to be like cardio, or I would consider it to be like 12 to 20 reps, you know, with limited rest, right? That's the best way to kind of grow those type 1 slow twitch fibers, or stabilization exercises. Whereas like, if we look at like our type 2A fibers, right? Those are kind of in the middle. What's up, Chris? We would go kind of like this. Type 2A, I would consider that to be, you know, a little bit closer to like 6 to 12 reps. So that's still relatively heavy, right? Limited moderate to limited rest, right? So a little bit of a combination of the two. No problem. Yeah, Wi-Fi happens all the time. And then I would consider like my type 2X fibers. That is like true, like explosive power, right? So repetition wise, I would consider that to be like, you know, 1 to 5 reps. Extended duration. Does that make sense, guys? Starting to see the connection there?
Yeah, I get it.
Cool. All right. And I'll say, just like from my side of things, like I've been mostly a runner for most of my life, but as I'm getting older, I'm getting out of the sort of endurance running and getting a little bit more into like weight training, because I want to have, you know, muscle mass that's going to last me, you know, into like when I'm, you know, you get older, right? And so like the older I get, the more emphasis I tend to put on like the strength training, while still keeping my heart like nice and healthy and doing plenty of cardio. But I tend to focus more on that. And that's why, like, you know, I've put a lot of emphasis on like strength training this year. And it's where like I'll do 2 months of working between like 1 and 5 reps. And then I'll do another 2 months of working between like 6 and 12 reps. But I don't really go any higher than that until I'll do 1 month of like stabilization training to kind of reset. And then I just rinse and repeat that whole sort of process over and over and over again. And so it's kind of getting the best of like type 2A and type 2X, you know, at different times of the year. So that is the general muscle fiber types. Now, you got a lot of different types of muscles in your body that have kind of different shapes. This is something you're never ever tested on, but you know, you've got what are called like fusiform type muscles. Those are the ones that basically are parallel to the tendon, right? They're running in the same direction as the tendon. So, you know, if you stretched it end to end like this, tendon here, fiber runs like this, it's fusiform. You've also got fan-shaped muscles, which basically have like, you know, the fiber will start really narrow and then it branches out like this. And then there's a bunch of connective tissue on the end. Those are your pectoral muscles, for instance. You know, it starts here and then it branches out and it's attached to this entire sternum here. A lot of different types of muscles out there you can see here that you're never really going to be tested on, but they all have like sort of different shapes and stuff. You don't really need to have any of this memorized to understand like how the body moves and stuff. But you do want to understand like, you know, where the muscles are pulling in like their individual directions. All right. Last thing we got to talk about. I already mentioned this a little bit earlier, but muscles can only pull. It's the only thing that they can do, right? They can only pull. They can pull and I guess they can relax. They can relax back to their original length, but they cannot push in the opposite direction. They don't have the structures necessary. So they can pull and they can relax, and they can pull, they can relax. So if that's the case, if we look at like,
What about your shoulders though? When you're doing like a military press, how are they pulling?
yeah,
Like
good question. Yep, absolutely. So what is a military press, right? It's shoulder abduction, right?
Mhm.
Abducting this bone here away as it continues going up, right? And if I were to go from the front, that would be shoulder flexion. So what's happening is this muscle right here, my deltoid muscle, is pulling like this, and that pulls the bone up, right? And pulls it up overhead like that. Meanwhile, my triceps are pulling like this. They're pulling this way.
The elbow in, yeah. So they're already in like a state of pull once you have the dumbbell like at chin level, right?
Yeah, when you're down here,
yeah, they're
that
already
muscle's lengthened.
Yeah.
Yeah, that's often why so many people have trouble going up overhead, is because we spend all day with, you know, that's also why our lats tend to be very tight, right? Think about like, what's the antagonist to this? It's the muscle down here that moves this way, right? So my lat is contracted right now. My deltoid is stretched right now. And if I go ahead, now my lat is stretched and my deltoid is contracted. And our body's just not very used to that. That's why so many people have arms falling forward as a problem, you know?
Yeah.
But yeah, the muscle pulls to kind of drag the bones around. That's why, do you remember from kinesiology? That's why we always say concentrically accelerates, right? Concentric means to shorten, right? It shortens to move it around.
Yeah. Okay. Thank you.
Yeah, no problem. So there we go. There's my picture. So this is how your muscles are kind of arranged, right? You can see, just go ahead and pay attention to this one on the left here for right now, but you can see like this muscle over here pulls this way, and this muscle over here pulls this way, right? So those have an antagonistic relationship to one another. They are sort of the exact opposite of one another. So we have to have a very clear language for how we label all this stuff whenever we're talking about whichever muscle is doing whatever job, you know? So what we call the main muscle that's doing a job, we call that the muscle agonist. Okay, it's the prime mover. The agonist is a muscle that is acting as the prime mover during whatever movement, right? So for instance, your glutes are the prime mover for hip extension. So hip extension is this right here, where I drive my leg back like that, or it would be, you know, coming out of a squat, right? I'm doing hip extension. My glute is the muscle that's primarily responsible for that. So I would say my gluteus maximus is the agonist for hip extension. Well, now it's like if every muscle, you know, can only pull, well, then I would, you know, if I only had agonists, I would contract one time and I'd be stuck that way for the rest of my life. So luckily, we have an antagonist muscle on the other side of the joint that pulls in the exact opposite direction. So let's say I want to, instead of doing hip extension, let's say I want to do hip flexion. I would turn my glute off and I would turn my hip flexor on, which would drive my leg up like that. So we've got one muscle that goes one way and one muscle that goes the other way. The classic example is your biceps and triceps, right? That's the kind of easiest one to kind of see, right? My bicep goes this way, my tricep goes that way as we contract. So that happens as an agonist antagonist relationship. So the agonist is the main muscle. The antagonist is the opposite muscle. It works in the exact opposite direction of your prime mover. So the gluteus maximus does hip extension. The hip flexor is an antagonist during hip extension. But if I were describing like hip flexion instead, if I were like, what muscle drives your knee up? I would say the hip flexor would be the agonist for hip flexion. That's why it's named that. And then I would say your gluteus maximus is the antagonist in this situation. So every muscle in your body can be an agonist or an antagonist. It just depends on what it is you're talking about. Mir, you were asking about the military press, right? My agonist for the military press would be my anterior and medial deltoid.
Okay.
And then my synergist would be my triceps. And the antagonist would be my lats. Now, same motion, but in reverse, if I did a pull-up, right, my agonist would be my lats and my antagonist would be my deltoid.
Okay.
So they all have opposites, right?
Yeah.
But they also all have stable helpers as well. And that's where the word synergist comes in, right? And synergy means, you're working together, you're in sync, right? These are muscles that assist your prime movers. So they're there to help, right? Triceps, for example, is a good example of helping during a military press. Shouldn't be doing most of the work, but they're there to assist, right?
Yeah.
Your hamstrings do a little bit of hip extension as well, but they're not supposed to do most of the work. So your hamstrings can drive your, work against the hip flexor, and they can work against those antagonist muscles. They assist the prime mover. And then you got stabilizers, which are muscles that kind of stabilize the body during certain movement patterns. So like your core muscles, right? That are there just keeping your spine held in place while you're doing all this like heavy lifting or barbell squatting and stuff, like think about like,
okay. So,
mid
like,
barbell squat.
Yeah, that's what I was going to ask right now, actually. When I'm like squatting really heavy weights, I feel like really wobbly, like in my core. So that means I should work on my core, no?
Yeah, I would start practicing that Valsalva maneuver we talked about. Learn how to take a big deep breath in, exhale, keep that tension, and then like don't lose that tension and go through your whole range of motion. It'll help with your stability.
Yeah.
I would also say like, if you even want to get like a weightlifting belt, so that you can have something to push against with your core, that will help with that stability as well.
Yeah, because I'm like really wobbly, like at the waist.
Yeah.
Yeah.
And sometimes you'll see people who wobbly at the knees. Everybody's wobbly in their different parts. They just need to learn how to stabilize. If it was your knees like waving like crazy, I would say you need to do like more balance exercises. So learn how to practice like a single leg squat, and then it will help, with that type of stability. It just depends on where your stabilizing problems are.
Okay.
But yeah, those are what are stabilizers. So again, any muscle at any time could be an agonist, an antagonist, a synergist, or a stabilizer. If I'm doing bicep curls, my bicep is the agonist. If I'm doing chin-ups, it's the synergist. If I'm doing push-ups, it's an antagonist. And then if I were just like doing like a lateral raise, which doesn't really involve my bicep, but it does create stability, now it's just acting as a stabilizer. So I always like to, whenever I'm describing these, I always like to use the Batman analogy. But basically, you think of like the agonist, the star of the show, that's Batman, right? And he's always fighting against the antagonist, who is like the Joker. And he's got his helper, the synergist, that's Robin. And then Alfred the Butler is there to emotionally support Batman. Tea and whatever when they get back to the Batcave. So that is your entire muscular system, guys. Any questions, comments, or concerns about the muscles? Joseph, Chris, how you guys feeling?
Good.
Love that. All right, I'll take it.
Just absorbing it.
Yeah, I'll take it. All right, cool. All right, well, let's go ahead and do hormones really quick. You will notice the notes are done. And it's just because, again, like I said, NASM does not teach hormones very well. It's literally like a paragraph in your book. So we'll just kind of go through the PowerPoint here. Let's just put this like that. So your endocrine system is the name for your hormonal system. And basically it's like a series of glands that like run throughout your entire body, and they secrete hormones. Now, this is under the control of your nervous system. But it basically works with your nervous system to control your body. So it's similar to the nervous system in that it's also a control system, but your endocrine system is under the control of your nervous system. So it's like the head honcho, but like, you know, it basically creates different types of hormones depending on the situation. So like you can kind of see, you know, obviously there's a little bit of a difference in hormones between like how men produce them and how women produce them, but most of these are generally the same. You know, most of what you're gonna, actually that's a great picture right there. Most of these are gonna create different hormones in different spots, right? So for instance, you get your hypothalamus, that's at the very base of your brain. You get your pineal gland, which is also in your brain, your thyroid, which is right here. You know, all kinds of different hormones out there that are created by each of those individual glands. So it's a system of glands that secrete hormones. So they live on like a host. All of your glands kind of live on like a little host organ. So for instance, like your pancreas, right? It kind of lives in your digestive tract, and then it secretes things like pancreatic amylase, but also secretes like you know, good Lord, insulin, insulin and glucagon, which are hormones that control your blood sugar levels. Actually, I realized I could just do this. So those are two really important hormones that are secreted by that thing. God dang it, there it is. So that is the hormones sort of the hormones host organ, right? Your adrenal glands, right? They live on your kidneys, which is where, like, you ever see like a boxer get hit in the kidney, or like, you know, just like in that, and they go down like a sack of rocks, you know? Yeah. And it's because like what'll happen is, number one, like that freaking hurts. But number two, it releases a bunch of adrenaline, which often causes them to like get really amped up. So the first time it happens, they'll often be okay, but there's so much adrenaline coursing through their body at some point, they'll often just like crumple.
Hey, so wait. Weird question. You think if I get the massage gun and just aim it at my kidneys, it'll release some of my adrenaline or what?
Maybe. I do not want to put my words behind that. I don't want to back that theory.
Yeah. Just punch yourself as you're working out.
Yeah. I mean, you do see people do that, right? I'm not even kidding. I mean, you guys have seen like power lifters.
Yeah.
They'll do that thing where they freaking slap each other like crazy.
Oh, I've seen that. I've seen them, yeah.
And what that does is that oh, hold on, actually, I think I have it. It's so weird, but it actually, I mean, truly is an effective method. No, the guy used a thumbnail and then didn't do it in the video. But no, they'll like slap themselves. You know, you see guys like do all that stuff. That's actually why people take smelling salts. It basically lights everything up because your body goes, whoa, something is wrong. Fight or flight mode. Boom. Right. And it gets into like really intense activity. So they do a lot of different things inside of our body. Some of them regulate growth of muscles, you know, like testosterone, for instance, grows type 2 muscle fiber in particular very, very well. Human growth hormone, right? HGH, that grows human tissue. It makes your bones bigger, it makes your organs bigger, it makes your muscles bigger. That's why we create so much of it when we're kids, and then it slows down as we get older. Insulin, that's created by your pancreas. Its job is to pull sugar out of your blood. Glucagon, its job is to release sugar into your blood. That's also created by your pancreas. So it goes in both directions. So we can see a lot of different ones. The big master gland is the pituitary gland. It's connected to your brain. And the pituitary gland, here's why hormones are so complicated. You know, with your nervous system, it's kind of like a light switch, right? It's like, I want to turn something on, flip on the light. I want to turn something off, flip off the light. But your endocrine system works a little bit differently. Your endocrine system will often create a hormone, which is its only job is to tell other glands to create more hormones. And then that gland makes a hormone, and then it creates another hormone in response. So it's like your pituitary gland might interact with your hypothalamus, which might interact with your thyroid, which might interact with your adrenal glands. And it goes like in that order. I call it the hormone hotline. This is often why we are so angsty when we are teenagers, because we start to create new hormones like testosterone, like estrogen, that we really weren't used to making before. And our body hasn't really figured out how to dial it in just yet. It's also why like women who go through like menopause later in life also feel a little unstable sometimes, because like their body is creating these hormones which are having like an impact on the body, but their body hasn't figured out how to dial it in yet, you know? Imagine if you had like a bunch of food coloring and a jar of water, and you're trying to get it like the perfect shade of purple. How do we make purple? A little bit of red, a little bit of blue. And it's like, that was a little bit too much blue. So you put a little more red in there, you're like, that's a little bit too much red. And you put a little more blue in it. And you're just trying to get the mix just right. And you're trying to dial it in, right? That's kind of how hormones are. You know, like your body's like trying to figure out how to like regulate those things right on. This is why if you've ever been driving and somebody cuts you off or veers out of the lane, you're like, God, you're right. And you lose your mind.
Yeah.
If you're like me. And then you're like, you're like, it's over. And they're gone. You're 2 lights away. It's over. And you're still sitting there like, you're just like, you're still mad, right? Like, it's like the hormones are still coursing through your body. The adrenaline, the cortisol, stress hormones, you know, all kinds of different ones. So there's a lot of different types of hormones that are running throughout your body. Your pituitary gland is responsible for releasing the ones that actually affect other hormones throughout the body. So for instance, growth hormone, that's made by your pituitary gland, so the base of your brain. And when you look at like what gigantism is, like Andre the Giant, right? Andre the Giant was like a pro wrestler, but he was huge. He was like 7 foot, 7'4", 520 pounds.
Big guy.
Big guy.
But Hulk Hogan picked him up though.
Yeah.
Yeah.
There's a famous picture of him holding a beer. Oh yeah, here it is. Check this out. This is Andre the Giant holding like a can of beer. That's crazy. You know, he was so big. And what he had is, what's that?
Looks like a kid-sized beer.
Right. He had gigantism. And what that means is basically he had like a small growth, or, you know, even like maybe a tumor, or maybe his brain was just shaped a specific way, but it was squeezing on that pituitary gland. And so it was just constantly releasing extra growth hormone. And that's what, you know, made him so big. Most people who have gigantism actually don't live very long, unfortunately, because it causes certain parts of the body to grow out of control.
I thought he was so big because he was taking HGH.
He was producing HGH naturally.
I don't know if they had that back then, bro.
So, well, I'm sure they could figure out a way to, well, yeah, good point. I don't know. But HGH, human growth hormone, is what I say when I'm saying growth hormone. That's what I'm talking about.
Yeah.
You produce HGH naturally, which is why people take it synthetically in order to, like, you know, experience extra muscle gain, which, by the way, is a terrible idea for a lot of reasons. It's a bad idea because, remember, growth hormone, I think they should relabel it. They should call it HSGH, human stuff growing hormone, because what it actually does is it grows anything human.
Yeah,
So it will
you don't
make
really control. You don't really control where
exactly.
what
So
it's gonna.
yes, it will make your muscles bigger, but it will also make you'll often get bone spurs. You'll often get diabetes because your pancreas will grow out of control. You will often get a weird one. This is the weirdest side effect I can think of with human growth hormone. You'll get carpal tunnel syndrome because that nerve in your hand gets pinched because the tube grows too big for the actual nerve to travel through. Hector, do you have a question, comment?
No, yeah, just about the HGH is just interesting.
Yeah, crazy, right?
Yeah.
So yeah, don't take this. I mean, doctors will prescribe that stuff. You know, if they see like a kid who has like a pituitary disorder, they'll often inject them with HGH, and it will help, you know, kickstart the whole process, and then they'll grow normally. You know, like there are ways to use these things, but again, they've been adopted and, you know, perverted and destroyed and so that's growth hormone. You've also got stuff like prolactin. Prolactin is a hormone that actually helps with like hair and stuff, but it also produces, like, you know, like breast milk and things like that. You've got ACTH, which is the hardest hormone to say. It's adrenocorticotropic hormone, but that's your adrenaline. You got thyroid hormone, TSH, that's thyroid stimulating hormone. So your pituitary gland creates thyroid stimulating hormone, which stimulates your thyroid to release thyroid hormone. And thyroid hormone will basically, you know, also speed up the metabolic processes in our cells. So if we're trying to speed up our cells, we use thyroid hormone. If we're trying to slow them down, we sort of use the opposite of that, which would be, you know, like dopamine and things like that. Follicle stimulating hormone, luteinizing hormone. You know, there's a lot of different hormones out there. So like I said, the thyroid gland is responsible for regulating your metabolism. That's the one that speeds things up or slows things down. You've also got your adrenal glands. Those are your fight or flight hormones. That's your adrenaline, right? That causes inflammation, or, you know, the opposite of that if it needs to. Depends on like what you're creating. You've also got like your testes, right? They produce testosterone. You've got women who have like ovaries, they produce like estrogen. For the record, both men and women, men produce testosterone and estrogen. Women produce estrogen and testosterone. We both produce both. But the levels are very, very different. And that's sort of what gives us our sex characteristics. You know, the more testosterone you have, the more body hair you get, the larger muscle mass you tend to have, the more estrogen you have. You know, generally that causes like loss of body hair in some ways. And then that causes like, you know, breast growth and tissue and things like that. This, by the way, is why what I'm saying right now might seem counterproductive, because if you are thinking of like people who have taken steroids, you're like, well, I've heard steroids will cause like, you know, like breast growth and stuff, right? You'll see like man boobs, you know? And it's like, well, the reason that happens is because they're taking so much testosterone that their body starts producing more estrogen in response in order to like level out that testosterone. So yes, that will happen because your body is sort of like responding to it. So you would think that like taking testosterone would just give you more androgen traits. But actually what it does is your body goes, whoa, we have way too much of this stuff. So then it starts producing estrogen in response. That's how they catch people who are on steroids in pro sports. They, because there's not a lot of like regulation in terms of like what natural testosterone levels are, but we do know what our estrogen levels should be. So when they find someone who's way out of whack, they know that like something is wrong, and they can test that through like a urine analysis. Glucose control, that's insulin and glucagon. So insulin is created by your pancreas to drive sugar out of your blood into your cells, and glucagon is to release sugar from your cells into your blood, and that way we have stored energy on the go throughout the day. Like I said, epinephrine, that's another name for adrenaline. Its job is like open up your airways, increase your heart rate, elevate your blood glucose level. Epinephrine is what is found in like an inhaler. And basically it tells your body to open up your airways because it thinks you are in the middle of, a fight for your life. So your body goes, if you get stung by a bee and your airway closes up because your body is having an allergic reaction, oftentimes they will inject you with an EpiPen, which has epinephrine in it, which is basically adrenaline. And then your body goes, wow, we must be in the middle of a marathon. Let's go. And it opens up all your airways, beats your heart like crazy, and keeps you from suffocating. But that's a fight or flight response. So, like I said, certain hormones produced by both men and women. Testosterone, men are going to produce about 10 times as much as that. That's why it's that's why men tend to be larger than women. Estrogen produced by the ovaries and the adrenal gland. Women are going to produce way more of that than men will generally. Cortisol is another one. Cortisol is a catabolic hormone. Cortisol tells your body to break stuff down, which and build fat. So cortisol is a stress hormone. It is a muscle destroying fat building hormone. And it's what we make when we're stressed, which is why meditation, warming up, cooling down, relaxing, exercising regularly is so good for cortisol, because it has an anti-effect on it. It lowers your cortisol levels. You ever hear those stories? They say that having a cat or having a dog will lower your blood pressure by 10 points. That's because when you have those things, you're happy, you're de-stressed, and that lowers your cortisol levels. So that's hormones in a nutshell. I know it's a very, very like drive-by explanation of them, but the big thing I want you guys to focus on today is the muscular system. It's made up of a whole bunch of different individual muscle fibers that are all bound together. Those muscle fibers have individual proteins that live in them, and those proteins like to bind together to create the actual contraction. And that is it for today, guys. So everybody, I want you to finish up reading chapter 2 today in your regular NASM textbook. And then I also want everybody to pop over to Canvas, log into day 2. Day 2, the muscular system, right? You can watch the review video. I will put up the video around 5:30 tonight. You can download the PowerPoint, download the notes. And then 15 multiple choice questions today about basically all of chapter 2. So I'm going to give you the first one here. Human movement is accomplished through the functional integration of, is it the cardiac, respiratory, and skeletal, nervous, and circulatory, digestive, muscular, and nervous, or muscular, nervous, and skeletal. Those are the 3 components of our kinetic chain. So you go down and click submit. It'll say, hey, you didn't finish out the rest of them. And it will show you what the right answer is. If you didn't put the right answer, it will show you what the right answer is. So you guys have access to your first piece of homework. Please practice it. Please get ready. We've got our midterm coming up on Tuesday. So any questions?
No, thank you.
Cool.
Oh.
All right. Well, fellas, you killed it today. Let me kill the recording here.
Clear.